Welcome everyone. In today's video, we're just going to go over an example of perturbation theory. Okay. Before that, we'll just remind ourselves, right? In perturbation theory, we define a reference and a perturbation, right, for a Hamiltonian. And the reference, right, is something we can solve. The perturbation is something that we don't necessarily know the solution to, right? And so the question here is, given this total Hamiltonian, what would be the best reference Hamiltonian, the best perturbation to define? Okay. So this first Hamiltonian, okay, is going to be, man, I keep on forgetting these negatives here, right? Right. So the first Hamiltonian is just minus h bar squared 2m times derivative. This is just the kinetic energy term, okay? So this is like the free particle Hamiltonian, and then my perturbation here is the Coulomb attraction term between electron and a nucleus, and then this cosine theta term, right? This, right, which is something could work, right? I know how to solve the free Hamiltonian, I know how to solve this, right? This has known solutions, right? And so I could potentially use this, right? Second part, I've added this a cosine theta, okay, to my Hamiltonian, right? I do not have this known solution to this whatsoever, so this is not really going to be good for a reference Hamiltonian, right? I need to know how to solve my reference Hamiltonian, okay? H naught here, again, it's just in some potential energy terms, no kinetic energy and stuff. This is, I have no idea how to solve this, right? And then D here has a kinetic energy term, right, plus this Coulomb potential, right, and this is the, right, this stuff together, this gives you the hydrogen Hamiltonian, right? Okay, and we do know how to solve the hydrogen Hamiltonian, right, and then perturbation A cosine theta, right? So D and A are valid ways I could do this, right? But one of the key things you want to do with perturbation theory is you'd like for the reference, like you want it to be the perturbation to be as minimal as possible, okay? Which means I would want to go with D here, right? Because I would want to start with the hydrogen Hamiltonian that I know to solve, and then just add this small perturbation A cosine theta to it, okay? And not start with a free particle system and then add the Coulomb potential plus a cosine theta, right? That perturbation is going to be not nearly as small as this a cosine theta correction would be, okay? And so that's why we pick D over A. Is again, we want the perturbation to be as small as possible, right? All right, so let's do an example here, right? Where I have some particle in a box system, where I have this perturbation that I'm applying to my system, where beta is just constant, L is the length of the box, right? Okay, and we're given here what the wave function is for the particle in the box system, okay? And then this integral here, which may or may not be useful, right? Probably going to be because we were given it, right? So the question here, right, is what is the first order correction in perturbation theory to the ground state particle in the box wave function, right? So the ground state particle in the box wave function is psi1, right, which equals square root of 2 over L sine of pi x over L, okay? And so the first order correction, right, is equal to the integral, right? In our case, it goes from 0 to L, because that is the, right, our system, right, exists from 0 to L, right? And so we just integrate from 0 to L, right, of psi1 v psi1, right, psi1 star v psi1, right, dx, okay? And so that is the integral we're needing to solve for the first order correction, okay? And so plugging in that information, we get this integral that we have to solve here, right? E1 is integral from 0 to L of sine n pi x times, you know, x times sine n pi x with some constants thrown in there. Okay, so just rewriting the integral, okay, and what I'm going to do is I'm going to pull out these constants, okay, beta L here, and square root of 2 over L, right, to get 2 over L times beta L, right, or that will simplify down to beta over L squared, right, and then I have an integral of sine pi xl times sine pi xl, or integral of x sine squared pi x divided by l. Okay. And so using the integral that was given in the problem, right, of the integral of x sine squared of alpha x, right, I can use that integral to simplify the above expression, right, this expression here. Okay. So plugging in that integral table, right, I get that this integral here simplifies down, not really that simple, but you know, to what's inside the parentheses here of x squared over 4 minus cosine 2 pi x divided by L, blah, 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 right? And then C here is a constant, okay? But I need to evaluate this at L0, okay? So, right, when I do that, the C is going to cancel, right? It's just a constant, right? So plugging in for x, right, L, and plugging in for x, 0, right, taking the difference between those two things, right? I have L squared over 4 minus a bunch of cosines and sines, right? And then I have, you know, the place where I've evaluated, right, x equals 0, okay? And plug in some zeros, right? Things are going to simplify down, right? I'm going to have a bunch of zeros multiplied by some stuff. Those terms are just going to be 0, so they go away, okay? Then I just need to use the fact of right, and so kind of simplifying this, we get this expression down here, right? And then all we have to do now is plug in for what cosine of 2 pi is, sine of 2 pi, and cosine of 0 is, right? Right? Well, sine of 2 pi is equal to 0, so this term goes away, okay? Right? And then cosine of 2 pi and cosine of 0 is just equal to 1, so those terms are left. And so, but we see here that these two terms cancel with each other, okay? I have plus 1 over 8 pi over L squared and minus 1 over 8 pi over L squared, so those cancel. So I'm just left with L squared over 4 is what that integral ends up being. So E1, once everything simplifies out, is actually just beta over 2. Okay, so a very simple looking thing, right? Start off kind of ugly looking, but simplify it down to just beta over 2, right? And so my total energy, right, according to perturbation theory, right, if I go to the first order correction only, would be, so for the ground state, it's h squared over 8 L squared, okay, because n equals 1. So the ground state, E1, right, this is, right, E naught, 1, right, the reference energy, and then it would be plus beta over 2, okay, and that's it, right? So that would be my total energy according to perturbation theory, where I've gone up to the first order correction for this particle in the box system with an applied perturbation of, right, that beta x potential, okay? All right, and so that is how one would use perturbation theory, okay, in practice. And perturbation theory is something that's often used in electronic structure theory, okay, right? So for multi-electron systems, right, what I have is my Hamiltonian can be split up into something kind of like the hydrogen Hamiltonian, right? So hydrogen Hamiltonian plus then this 1 over like R12 term, right? This electron repulsion term, right? I can consider this as the perturbation, right? So this is my V and this is my H naught, right? And then I can use that to try to get corrections to the true energy for my system, right? Where I can use my reference, say like hydrogen Hamiltonian, okay? So that's it for perturbation theory, all right? And the next kind of videos and things like that we'll start talking about, we'll actually be talking about other aspects of electronic structure theory.